As you can see, I'm trying to use several different ways to record my own lecture so that I can combine these videos together. Then, if you know, last year I taught this course before, the same time the spring in 2025. So the video are all on YouTube. So feel free to watch last year's video. The skeleton of this year will be pretty much the same, at least for the first half of the semester. Now I try to extend more content towards the second half of the semester, and to go a little bit more advanced that fits like a PhD level course. Okay, so well, the code is there again. Well, at least it's not part of my recording, I guess. So how many of you are undergraduate students? Four, right? 4 students. Okay. How many of you are master? Okay. 3, 4, then 5. Okay. Then the rest. How many of you are PhD students here? Okay. So roughly the same amount of undergraduate and graduate, master and PhD student. That's good. So this course is Advanced Computer Architecture. So I guess most of you have never taken a computer architecture course, right? How many of you have taken a basic computer architecture course? Okay, there are several of you. So how many of you know what is sequential logic and combinational logic? That you're comfortable with this content? Okay, a little bit. Okay, so typically when I say advanced computer architecture, we do not teach sequential logic and combinational logic, but because most of you do not have this background, I probably will spend 2 weeks time to review those content. Those are not super important for this course, but it's the basics for you to understand that no matter what advanced features that we're designing in computer architecture, they are eventually implemented with basic features. Okay, so what this course is about, this is a fully lecture-based courses, so we're not expecting read papers or doing presentations. And we're going to cover topics like starting from Boolean logic, combinational logic, sequential logic, probably Verilog, simulation, RISC-V ISA, computer CPU core architecture, branch prediction, speculative execution, DRAM, cache, coherency and consistency, network on chip, and especially GPU architectures. So a lot of topic. Then last year we do not really have DRAM there covered. Then we do not have much speculative execution. We didn't cover Verilog. Probably this year we're not going to cover Verilog again. Then we covered coherency. We didn't cover consistency. Let's see if we have time to cover consistency or not. We didn't cover network on chip, but this year that's something that I really want to add. Okay, and if you watched the video last year on GPU architecture, I didn't have slides. I just write it using Blackboard. So and this year I'm going to make slides for it. Now we're going to have assignment and quizzes. Quizzes are more likely to be on Google Forms, so that you can just fill in a few selection questions, then you immediately can get a grading. Okay, then simulation is a core topic. Now I'm going to teach you how to run computer architecture simulations. Then for you to verify if you fully understand the idea, I ask you to write some simulation code. Okay, ask you to write some simulation code so that you can, like, say when we learn cache, I may ask you to write some cache simulation code, so that then I know, oh, you understand how cache works basically. Then in general, I consider you can use generative AI now either to say ask questions, what is a cache, how does way associative cache works if you do not understand the concepts in the lectures. If you write code, totally it's okay to use generative AI. Generative AI are everywhere. Now you can use it to help you learn. And for simulation, since we're going to use the Akita simulation framework, that is a simulation framework developed by me, where you're going to use the Go program language. So if you have no Go experience, don't worry, it's easy. It's easier than Python. So especially when work with generative AI, it's probably you just don't need to learn. Just see examples and write code. As long as you can read it, it's good enough. So on the syllabus, there's a textbook. There's no need to buy the textbook. I will cover all the content, and I will. If you want to buy it, that's okay. It's a very good textbook that I learned the basic things from that textbook. But I will also provide further reading recommendations. So that textbook is undergraduate level computer architecture or even digital design level. It's a basic computer architecture textbook. For some advanced features like consistency, network on chip, there are very good textbooks there. So I may recommend reading. Then you can get electronic version from our library. Okay, so I won't cover the syllabus again. So I'm basically just directly going to cover real content, starting from what is computer architecture. The syllabus is there online. I think you are all you can all see the course website, and you are all in the Discord, right? So that's good. So if you have questions, let me know. Now, what is computer architecture? Then you probably have seen this type of technology stacks. Then starting from application to physics. Now we want to use physics properties. For example, we have electrons, we have neutrons, or we have magnets, we have electricity. Those are all physics properties, or something fall from above to bottom. Those are physics properties. And we have applications. For example, we want to write documents. We want to write. We want to have AI to help us think. Those are applications. Those are something that we want to do. So we want to bridge the physics and the application to use those physics properties to solve applications. For some very basic cases, now we can almost directly use physics to solve problems. For example, that's a level and that's a compass, right? So we can directly use the magnets to point to north and south. Then we can almost directly solve the problem. Not that hard. Then we don't really need a technology stack. Now, a single person may probably be able to produce these type of tools. But for computer architecture and for the whole computing domain, so probably there are some people working on AI algorithms, for some people working on making those chips, for some people working on producing these chips. There's almost impossible for a single person to work on everything. So we divide this whole technology stack into stack frames. We divide into individual tech layers there in the technology stack. So some people work on this layer, some people work on that layer. Now, so if we can define the interface between the layers, then people can collaborate with each other and can help us use the physics properties to achieve or design the goal. And this is the computing technology stack. I think this is definitely an oversimplified version of a computing technology stack. It's probably a stack may not be the best way to describe the computing landscape this year. There's probably a graph that there's so many domains that that people work on different things and then they combine so that we can run generative AI today, right? But this is a simplified version that we can see. We typically call it when it's closer to the application, we call it on the top of the stack. When it's close to the physics, we target on the bottom of the stack. There's no good or bad, it's just different things. So for example, at the bottom we have devices. Now we typically call transistors, right? So those super small things that are doing on and off switches. Now the gates, and gates, not gates, at least that's something you should be familiar. The microarchitecture is how these chips are designed internally. Now we have instruction set architecture. We'll explain this later. Now from here on top, we'll start to go to the software domain. Start from here, we start to go with the software domain. For example, we have assembly and machine code, right? The very basic software that we're using to communicate with the hardware. Now we have operating system, we have program here, program language here, and algorithm. Those are some course titles that you may have already taken. Now what is instruction set architecture? Now, especially when we talk about computer architecture, we say it's somewhere between this region. Then instruction set architecture, or ISA, you probably have heard of this name, is a protocol between the software and hardware. So probably you have heard these terms of x86 or or AMD 64 or ARM or IBM PowerPC or RISC-V, those are all protocols. Those are defined, say, okay, 00001 means to add operation, add two numbers together. 002 means a subtract operation. That means to minus from one number to another, minus a number from another number. So this is the protocol between software and hardware. Then if you go back to the early ages, by that time we don't really have this layer. By that time we probably have much fewer layers, right? Then by the time then people use a tape of paper, those papers with punch holes. Then those punch holes directly represent zeros and ones. Now we don't really have that number. So in that time, every computer may have their own instruction set, their own program language. So if you program for one computer, then later on we have a new computer. Then the software, you totally need to write new software. And people do not really care that much because software by that time was pretty much disposal, that you use one time, then you get the result, and then you're done with this software, right? So, but later on we want reuse, we want to save time. So we write one program, we want to use again and again. And especially when we want to have new computers, then the program still runs. Then we added this layer. This layer is probably the most stable layer in the whole architecture, right? In the whole stack. Like consider devices. We have 3 nanometer, we have 7 nanometer. It's changing really fast. Then we have something like MOSFET, FinFET. You don't really need to understand what those things, but those are totally different devices, right? But consider how difficult Apple switched from PowerPC to x86. That's very early ages. Then Apple switched from x86, from Intel CPUs, to ARM CPUs, to their own CPUs. Then Apple was the successful example. There are so many unsuccessful examples. It's a very high cost. Because if you change this thing, you need to redesign everything below and redesign everything on the top. That's a lot of work. Okay. Then another separation of this technology stack. Then you probably have heard of these departments. Now we at Marriott, we only have computer science. So in computer science, we probably have to cover more things. But in some universities, they have electrical engineering, they have computer engineering, they have computer science, right? So where are their boundaries? They typically consider anything below instruction set architecture or electrical engineering. Although this year's electrical engineering department are doing AI. But typically we consider the basic things, device level or electrical engineering. Computer science are on the software side, right? But if you talk about computer architecture, it's typically the system side to microarchitecture side, right? So it really depends on how the departments are defined. Now, in terms of computer architecture, we're talking about this middle layer, right? So when we talk about this middle layer, you consider it's like the core muscle of a human, right? If you want to, say, play tennis, right? You need to hit a ball hard. Then you really need your core muscle. So look at here. Then applications keep changing. Now, right? We have generative AI. We have many new things like the image generation. Then we have new software appearing almost every day. Then we have new devices: 7 nanometer, 3 nanometer, 2 nanometer, or something like the compute in memory, right? So there's so many things that happens at this layer. So they develop rather independently on their own. They just want faster and faster, smaller, low energy. And then this side, and they just develop on their own, just say, oh, we want generative AI, we want to do something. Then computer architecture in the center is connecting these two parts. So whenever there's some new application, new algorithm, we have to think, oh, how we can make those algorithms run faster. Then whenever there's new hardware, there's new device, we need to consider how we can use these things to make the top layer run faster and run more in a more secure way. And actually, then, as I say, it makes things run faster. It's not only about faster. Just think about AI, right? Think about why AI was not a thing even before 2012, right? In what happens in 2012? Do you know why I say 2012? So 2012 marks one thing, is the development of a convolutional neural network called AlexNet. Okay, AlexNet significantly increased the accuracy of image recognition. It just like another level, right? Is whenever the quartz watch, right, the watch that runs on the crystals, right, is so much accurate than mechanical watches, right? It's just suddenly a new type of animal entered the game. That's AlexNet. Then starting that point, in a few years, you see image recognition are very mature and in commercial products, right? Like face recognition is probably in every camera after that point. Then, so 2012 is definitely a big thing. It's probably more important than the year when ChatGPT was released. So why that thing, AlexNet, started in 2012? There are two big reasons. One is ImageNet. ImageNet is from Stanford. It's a big data set. So people start to care about the quality of the data set, the training set. And another thing is people start to use GPUs to do calculation. If you consider GPUs versus CPUs on AI workload, it's not because the CPU cannot do it. It's just because CPU is slow. But if we can accelerate it by 10 times or 100 times, think about 100 times. If it's a year's task, that you can reduce it to 3 days, that's you're turning something impossible to possible, right? So so in this sense, computer architecture are enabler of new technologies. Okay, so those are the point of computer architecture and why we study computer architecture. So as we say, computer architecture is in the center of this technology stack. I often compare computer architecture with, so you probably have heard of these people who write Verilog code, who design circuits. Those are rather entry-level jobs. Now, what's the jobs for computer architecture? So computer architecture are typically considered a slightly higher level jobs, are research type of jobs or manager type of jobs. And it can be compared with something like a software developer and a UX developer. So UX developer there is it's a designer and also a project manager. So in big companies like AMD, NVIDIA, Intel, they have developers who write Verilog code that implements the next generation of their software. Right? They also have computer architects who looks 1 generation beyond, 2 generation beyond. They're like 3 years product line, say what features we want to implement. At this layer, you just probably have many ideas that not all the ideas may work. You just have to discard all those ideas. Then eventually you decide what are valuable, what are practical, then you give it to the entry-level jobs or Verilog writers to implement the circuit. Okay, so at this sense, we really need to understand a lot of things. We need to understand what happens at device level and what happens at application level so that you can really design the right thing. So I don't want to waste time, so let's start from transistors and see there are many things that we need to consider when we design computer architecture as a higher level design. So transistors, we all know transistors are the building blocks of chips, right? So at the beginning, transistors are something that looks like this. These are not even the beginning. These are like 80s or 90s, and people are built like radios, and they just use this type of devices. So whenever we have a transistor, we typically say it's a 3-pin device. So 3 pins, 1, 2, 3, right? So they have either output or input. They have just connected to outside world with the 3 pins, right? So when we talk about digital logic, digital logic we consider 0 and 1. So it's either 0 or 1 that is passed into each pin. Okay, so when we consider pins, it's actually a very important concept in computer architecture. So it's something similar to when you are doing visualization. When you're doing computer or interactive visualization, the pixels on the screen is actually a limiting factor. Let's consider this one is 1024 by 768. That's older standard. But That's about less than 1 million pixels. So that means you cannot really show more than 1 million elements, right? That's a hard limiting factor. When you consider chips, the number of pins are how fast that this pin can communicate with the outside world. That's also another hard limit that people easily ignore. It's a 3-pin device. Now you probably have heard of these vacuum tubes. And those are the early type tubes that are built in early computers. So I just want to introduce how they work. So this is a vacuum tube. Internally there's no air, there's nothing in it. Right? It's a piece of glass. So it connects with 2 powers. Actually, it connects with 2 powers, right? So this is one thing. This is the control side, the control grid, and this is the I would say this is the load side. That is where you put a bulb or something. Then we use the signal on this side. We want to use the control. So roughly speaking, it's a switch. Then we want to turn it on or off. Now how it works is there is a control grid. The control grid, now if this power is connected, it's heating this control grid. It heats it up. Whenever it heats up, then these electrons can flow from this side to the other side. The I don't know the exact physics here, but you just can treat it how it works. Whenever the electrons can flow from one side to the other, the circuit is closed, and then this side is connected, right? So even today, we want to have a transistor works in a very simple way. We have a control signal. It can be either 1 or 0. Let's say 1 means to connect this circuit. 0 means to disconnect this circuit. Then that's simple. That is how transistor works. Although transistors can be super complex, but for computer architecture, that's the basic things you need to understand. Now with this, if this can represent a 0 and a 1, then we can combine these transistors to make logics, right? So later on, we don't use vacuum tubes. What's the problem with vacuum tubes? It's really big first, right? Just think about the early age computer. It takes the whole room or the whole building and only can store hundreds of bits there. Then it's very energy consuming. Consider there are 2 things. Heating up metal takes a lot of energy. On the other side, this is a circuit that is keep flowing, right? So the energy keeps being wasted. It's like a short circuit here. That energy is wasted on this side, right? So we don't want this energy keeps running. We want to save energy. Just consider energy is probably even more important today than performance. Why is it? Because if you consider today generative AI, you probably have heard of this. Generative AI, that the bottleneck of the capability of generative AI is electricity, how much electricity that we can generate, right? So if we have more electricity, we can have more powerful AI. On the other side, this electricity, no matter like what type of devices, if we put electricity in it, if like my laptop takes like 25 volts of power, the energy, the 25 volts is eventually turned into heat. Then we even need to have more energy to bring the heat away. So we either need to use air conditioner to bring the heat away, or we need fans or to blow the heat away. Now even we blow the heat away, we need air conditioner to bring it out from the room, right? And also sometimes we can just build the supercomputing center near a river, so the river water can bring the heat away. There's also proposal that put a data center under the ocean or put it in the outer space. So there are many different proposals that consider how to bring the heat away. So I asked someone who built a data center, they say it takes more energy to bring the heat away than to power the computer itself. Okay, so and because we can bring the heat away in a certain speed, we cannot really generate the heat faster, too fast, right? If it's generating heat too fast, the temperature of the chip is too high, it's below a certain degree, then the chip will melt. So we have to turn off some cores or some part of the circuit so that we can within the power limit. Now because of this, if we can reduce the energy consumption, we can have more parts of like more cores enabled, then we have more performance, right? It's not really about conservation. It's not really about environmental. Like definitely environmental is a big consideration, but even if you just consider performance, you need to consider energy consumption. Okay, so then later on they use BJT. BJT is a semiconductor. Before that is not even semiconductor. BJT is semiconductor. Then so there's 3 layers, 3 ends: emitter, collector, and base. Then the base is the control. So if the base is connected with 1, then these parts are connected. If it's not 1, if it's 0, then these parts are not connected. So BJT solves the heating problem. Then we don't need to heat up metal to enable it, but it's still current driven. It's not totally bad. It's still useful in some cases. It's just not the technology that we use in modern computer chip design today. What do we use today? You probably have heard of this thing called CMOS. It's called complementary metal oxide semiconductor. Okay, let me introduce this part first. Metal oxide semiconductor. So this is like the side view of, I would call it something called a gate, but we can just focus on this part. So we have a P substrate, physics. Don't worry too much about physics, okay? Then we have an N well and another N well. Then here is an oxide, right? It's not like the electricity cannot go through. Now here is a piece of metal on top of it. Okay, if we apply a voltage on G, there are some magic things happen in the semiconductor here. Then this N and this N are connected together. Okay, if we do not apply a voltage here, this N and this N are not connected at all. Okay, so this is how it works. You just don't consider what's N, what's P. Just know if there's a voltage, these two are connected. If there's no voltage, these two are not connected. On the other side, it's the other way around. If there's no voltage, these two are connected. If there's a voltage, these two are not connected. Okay, so this is why we call it complementary. So you can consider one side is an NMOS, one side is a PMOS. Don't even need to consider which part is NMOS, which part is PMOS. Just see if there's a circle in terms of like circuit annotation. This means kind of a not sign. That on the input side, that means if it's 0, it's enabled. On this side, if it's 1, then it's enabled. Okay, let's look at what's going on here. Let's say if A is 1, okay? If A is 1, so VSS is ground, is 0 volt. VDD is 1, is 5 volt or 1.3 volt. It depends on the definition. Sometimes it's 12 volt. Then if A is 1, this part is not connected, and this part is connected. This part is not connected. Just when it's not connected, just ignore this part. Just assume this part is not even there. Okay. Then this part is connected with Q, so Q will equal VSS. Question?
So this is like a electrical version of a mechanical switch or water faucet.
Yeah. Yeah. It's a signal controlled switch. This switch is connected. Just consider there's a wire. Okay. Only consider there's a wire connecting these two. There's no wire connecting from here. Okay. So it's 0 volt. Then 0 volt goes here. If it's 1, if it's 0, this part is connected. Just consider there's a wire. There's no wire here. Okay, it's disconnected. This part is connected. Then Q equals VDD, and that means Q equals to 1. So summarize this. If A is 1, Q is 0. If A is 0, Q is 1. Okay, so that's a NOT gate. So Q always equals to the other side of A. Okay, comfortable with this design? So what a problem it solves? There's no current here. There's only voltage control, right? So this part is not connected. So this metal is totally disconnected with the rest of the circuit. And this metal is the white part on the top. It's totally disconnected with the N part here. So there's no current going through. VDD and VSS are never connected. Okay, they're never connected. When Q is connected to VSS, its voltage drops to 0. When VDD connects to Q, the voltage rises to 1, but there's still no current going through. So what's the energy consumption? And typically, we say a chip consumes two parts of energy. One is dynamic energy, one is static energy. Static energy means there's no pure isolation, right? There's always some voltage, some electrons goes from VSS to VDD. It's the current goes the other way. So that's, but in CMOS, this is really small. And no matter it's 1 or 0, it's still that small. It's still static, right? But if you consider BJT, if it's 1, then this is connected, then consumes a lot of energy. If it's 0, it's not connected, it's not consuming much energy. So here, the static energy is really slow, no matter it's 1 or 0. Then what's the dynamic part? Those are switches, right? Switching the state means some electrons goes from here to there, then there's some energy consumption to switch on and off these gates, these switches, right? So those are dynamic energy. And static energy and dynamic energy, those are two parts of energy consumption. And summing up these two parts of energy is the total energy consumption of a chip. Okay, so today, we definitely want to reduce the static energy. And static energy today is actually rather low these days. It's mainly dynamic energy consumption. Now, if you look at the NAND gate, I think I can leave it as an exercise for you to analyze how this NAND gate works. But just consider if A is 0, B is 0, this part is not connected, right? And A is 0, this is connected, both of them are connected, then the output is 1. 0, 0, output 1. So it's AND, and get the other side of AND, flip it. Okay, you can do it as an exercise. I want to go too deep on here. Any question? Okay, so then consider early days BJTs or transistors are in this way. You probably have used the breadboard to build a circuit. You know the pain. Then if you have built it, then even a breadboard, the largest breadboard, like when I was undergraduate student, I built a 2 breadboard, and that's basically 2 full breadboard. That's basically a clock, 24-hour clock. That's the maximum I can do. Then using PCB is much better because we have those circuit pre-built. So in this way, it's not very likely to build a whole very complex chip in this way. So then people start to build integrated circuit. An integrated circuit was first built by people from this company called Fairchild. Although this company is not there, it's still a legend because there are many people coming out from this company. Is becoming very important person and very important other companies in the later time. Then people start to build this thing called very large scale integrated circuit, or IC as integrated circuit first, and they build larger scale. Then larger scale, they have large scale integrated circuit. Then when they grow very large, they just call it very large scale integrated circuit. So VLSI is a term today that people probably do not just spell it out, but it stands for very large scale integrated circuit. This is what it looks like in this way. So you don't really have to understand too much about that, but in these different colors mean different things. For example, red may means P-well, green may mean N-well, and this blue part may means copper, right? Just coppers are wires that connected. Then those X are coppers that goes down so that it can connect with the bottom layers. So don't worry too much about this. And when people consider this, is basically some like the process of going from breadboard to PCB. Like we want to be able to print the circuit into something that is really small. Okay. So later on we'll talk about how these can help making a chip and how chips are made. So then very large from Fairchild there comes two people. One is Robert Noyce, one is Gordon Moore. They started this company called Intel, which is like really the company that make VLSI or integrated circuit a very important business, practical business. And if you heard of Gordon Moore, this name, you should be very familiar with one thing, that's Moore's law, right? And that's what he proposed. Now, he proposed this law at a very early age when the integrated circuit may only have a few, like tens or hundreds of transistors there. So what is Moore's law? Yeah.
It's basically that there will be a doubling of transistors in every single device every year. They'll get smaller as well.
Yeah. Okay, so let me repeat. So Moore's law at the beginning is in this form. The number of components per integrated circuit can be doubling every year. That's the original form. Then later on, this is slightly changed. The computer performance will roughly double 18 performance, but this performance is today we measure by number of transistors. So the number of transistors on a computer chips doubles every 18 months with no increase in power consumption. We'll talk about this part later. This is more on Denard scaling part. But this 18 months is also a modified version that later on as it fits the curve. So then this is, so since 1990, people are saying, oh, we're close to the end of Moore's law. Close to the end of Moore's law. They say, oh, our transistors are 1 micrometers large, like 1,000 nanometer large. How can it be smaller? Then 25 or 35 years later, we're still saying we're at the end of the Moore's law. But Moore's law, is it still working? So there are two figures here. One is from Wikipedia, one is our own data. Okay. So we have a data set that pretty much summarizes all the CPU and GPUs that is commercially available on the market, and if they release their technical information. Now you can see on Wikipedia, it's still rather linear, right? So if you consider on this side is exponential, right? It's logarithm, log scale. So then it's growing exponentially. Now here from our own data, it also shows that it grows exponentially. Now I can also even explain what's going on here. It's basically when Intel, like the later version of Intel, they stopped releasing their number of transistor information. And since Moore's law stopped a few years, now when either they start to release or AMD is catching up, then this trend is still kind of growing. Okay, so Moore's law is still there. Now we know how this is achieved is by making the transistor smaller and smaller. Now how small is our transistor? You may probably heard of this transistor size that a few years ago we have 7 nanometer technology. Today probably the mainstream is 5 nanometer or even 3 nanometer. So probably next year you can get 2 nanometer technology. But I have to say this number of transistor size is more and more a commercial term. It's not describing the real transistor size anymore. Okay. It's not really describing the transistor size anymore. It's more, especially this is TSMC, the Taiwan Semiconductor Manufacturing Company. It's their terminology. Intel follows a different terminology. That's why Intel is still in the 14 nanometer era. And even Intel is going more and more commercial so that their number doesn't really represent the size of the transistors. But this is a summary of density per chip. Then we simply just calculate from our 4,000 chips, right? The commercial available, the number of transistors and the die size. The die size is how large the chip is, right? Just so that's a transistor per millimeter square. Then pretty much you can see for every transistor size, and we only take the TSMC data. TSMC is something called a foundry. Foundry is the manufacturer of the chip. So there are three major foundry in the world. Intel, they can produce chips on their own. Then Global Foundry, and another one is TSMC. Definitely today, TSMC is probably the best. And Samsung can also produce, and ZTE can also produce. There are several other companies, but their technology cannot compete with the other three. So, but if you look at TSMC data, then pretty much like for every technology, for every process size, their scope is very small, and that their density is consistently increasing, right? And even 7 nanometer is much higher, much better than 12 nanometer technology. So if you compare with atom size, so what atom size, how large is the atom, is typically 100 to 200 picometer, right? So picometer is one level below, so 1,000th of a nanometer. So if you consider those are tens to hundreds of atoms per transistor, that's it. So just it's pretty much atom level control. So are we at the end of Moore's law? Then if you consider the number of atoms that we control, probably yes. But if you look at the trend, then probably we can go with probably a few tens of years. So how are chips made? How can chips are made so small? And I need to review the whole process so that you can know there are some fundamental constraints of this whole process, so that you know why we design computer architecture in this way, why we need to care about number of transistors that much, care about energy consumption that much, and care about the die size that much. So transistors are starting from silicon crystals. Silicon crystals are made from sand. So it's a magic converting from sand to chips, right? But we typically start from here. TSMC just buy silicon crystals from other companies. Then these silicon crystals are super pure. That's 99.999 or many nines is much more pure, much purer than the gold that you can buy today. So they really need super pure silicon, because if there's something that is not a silicon atom there, the whole chip may not work. So it's very important. Now with this silicon crystal, they slice it into wafers. Okay, so it's definitely comparable to those cookies, crackers as wafers. Then how large is this wafer? These wafers are typically like smaller than 20 inches in diameter. So consider a medium-sized pizza or small pizza. That's about the size of a wafer. Okay, so how large is a chip? Right, the largest chip today, if you do not consider something like AMD Threadripper, a chip is about, let's say about a cap. Like that's a rather large chip, right? A CPU chip or something. That's about the cap of this whiteboard pen, or two of them. That's a very reasonable CPU size. For GPUs, that can be slightly larger. So how it works is we first really produce the chips on there, then we slice them. Okay, make them smaller ones. And how these chips are manufactured is a process called lithography. And this is, if you heard of this company called ASML, then those are the masters of lithography. Then they produce these tools that are so precise that they control atoms. So how it's done? Now we prepare a wafer, right? We slice it. It's super clear that use a lot of pure water to clean it. Now we first put a coat of photoresist. It's a gel, right? and we pre-bake some technology just make the gel more persistent. Then we put a line and expose. What does that mean is we put a mask on top of it. So consider how precise this mask is. A wire is nanometer level, number of atom level, right? And we put a mask on top of it, and we use light to cast light on it. So these photoresist material are sensitive to light. If light is cast on it, they will disappear. Okay, they will disappear. So then we have this thing. So probably here are the parts that we want to N-well or P-well or copper or something, right? Then what they do is they basically use a chemical to wash away so that it goes deeper, then they can build things on it. So they probably also use some, use as a target to have a particle stream to heat it so that they can start to build things on top of it, right? So consider this thing. This is so small. It's so small. Like you probably have heard of this light may scatter when you go through a very narrow gap, right? So how much scatter they have depends on the wavelengths. The smaller the wavelengths, the less scatter they have, right? So that's why you have probably heard of this extreme ultraviolet today. Ultraviolet, extreme ultraviolet. Those are technologies developed by ASML. Because the more towards the ultraviolet side, the smaller the wavelengths, then the more precise that we can control these gaps here. And also, they have done lots of crazy things to make it precise. For example, they can really not, even the gap itself, they can really not have control a few atoms. So what they do is they first etch this side. They first only cast this side. Then they put another layer, then each another time, so that they can produce a very thin wire in their on their chip. So this whole process is very precise. It's very difficult. Then after that, we have something called packaging. So don't underestimate the power of packaging. It's actually very, very important. So early days, we have this packaging that the pins are on the side. So packaging is basically the chip is in the center, then we use wires to connect with the pins outside. Then we use a piece of plastic on top of it. Now you probably have seen those toy watches. If you open those toy watches, there's a big black thing, like a round black thing. So that's the easiest way to do packaging. So they put the chip directly on top of the PCB. Then they drop a piece of plastic or wax or something just to seal it so that it's not interfering with the outside world. So, so even like this, it provides a basic level of protection for the chip. Even this, if you touch the chip, the plastic part of the chip, like the static electricity may damage the chip. But that's something very important. Then these pins are on the side. But consider if it's on the side, how many pins that we can have, right? Then later on, we have ball pins underneath. So today, how many pins are there? Can you guess how many pins are there in AMD or Intel CPUs? It's a rough estimation. Yeah.
Probably 3 billion devices run job. I'd say like probably 10 billion.
Pins?
Oh, pins.
Pins. How many pins?
Probably like 20 billion.
And that's a little bit too much.
Okay.
Yeah. So look at here. So basically, on this type of device, it's on the side. Yeah, go ahead. A couple of hundred is lower estimation for lower end chips. That's reasonable. So higher end ones are 1,000, 2,000, that level. Okay. So consider this on the side is probably tens of them. So with the bottom ones, they can have thousands of them. But even with thousands of them, that's the number of bits that you can communicate with outside world per cycle. Okay. Actually, they can do more. They can send more bits, but probably in each cycle. In 1 gigahertz, if it's 1 gigahertz, that's 1 nanosecond, right? 1 nanosecond, then they can probably send out 16 bits out from one pin. Question?
When you say send, are you talking about using the process?
Yeah. So they send out data in many different ways. For example, a CPU may read and write memory, right? The memory and the memory are inserted on your motherboard. They may send video signals to your monitor, right? They may send signals to the Wi-Fi package. They may send signals to the hard drive. So those are all how CPUs communicate with the rest of the world. Okay. So packaging technologies are developing on its own. So for example, today we have this packaging called multi-chiplet or chiplet, multi-chip module packaging or chiplet technology. So consider today the highest end CPUs and GPUs are all chiplet-based technology. So if you consider one thing, when we say Moore's law, the original Moore's law saying the number of transistors on one chip doubles every certain number of months, right? Does this count? This, like by the original definition, this doesn't count because there are so many chips there, right? But they can combine the chips in one package, in one product. So that's why in this figure, if you look at this figure, there are many of them on this corner are multi-chip technologies. So Moore's law is growing in many different ways that Gordon Moore himself cannot imagine by that time. There are many different creative ways to continue Moore's law. And we'll talk about why multi-chip module is so important this year. Then TSMC also announced a technology called wafer system on wafer, SOW. Then it should be announced in 2027, so next year. So what's the technology? So you can see here, this is called a package, and this is called an interposer. Sometimes we call it interposer, sometimes we call it substrate. What is an interposer? It's basically a layer that provides communication of these chips, right? So we say chips, there are three tiers of network: in-chip network, in-package network, and off-package network. So each layer consumes, like the lower the layer, they consume more energy and they're slower, right? So with the interposer, it provides faster network than going off chip, going to the PCIe bus or something else, right? That's why this technology is so important.
So is this the same thing as the system on a chip?
No, system on chip is basically you have different modules, different IP cores. What is IP cores? For example, Wi-Fi module, memory controller. Those are different IP cores, or CPU cores, GPU cores, accelerators. Those things are integrated into one circuit. That's a SoC, system on chip. So a chip it's not only about the CPU, it's everything. So that's system on chip. Then system on wafer is more like a packaging terminology. So it doesn't really have to be a term. It doesn't really have to be a system. For example, a manufacturer may just want to produce a super large GPU. Yes, they can. They just many GPU chips, then they put it on a wafer, right? That's possible. So it's just different terms in different domains. But as you can see, the interposer is a piece of silicon. What's the largest size of a silicon? It depends on the wafer, right? So the wafer is the maximum size of a silicon. That's because that's the piece that we can slice. So system on wafer is probably the largest that we can imagine on this type of technology that's expected to deliver high performance communication between chips. Probably we can see super expensive devices coming out in 2027 or 2028. When we talk about chips design, we have to talk about defects and yield. What is yield? Yield is on a piece of wafer, right? This is a wafer. And when they produce chips, they actually produce all of them together, right? They produce all of them together. Then later on, they slice it. So there are several things. So sometimes just imagine a piece of dust or a hair, a piece of hair that falls on it. A hair is micrometer level or even millimeter or micrometer level, right? So it can hit thousands, millions of transistors. Like pretty much a hair falls on a piece of chip. That chip, there's no way to use it. So we talk about like dust may just randomly fall on these wafers when they manufacture. Even they have super clean rooms that have airs keep blowing from top to bottom. They have to wash and then put on those special clothes all day long to work in a super clean room. Then low yield may be always there. And especially when we have smaller and smaller transistors, the yield is getting lower and lower. So if you consider we build a wafer and many of them we have to discard, the cost of manufacturing a chip is rising, right? But if you consider like where this dust falls, it's a distribution. It follows something like a Gaussian distribution or like a 2D Poisson distribution. Then the larger your die size, each chip, the more likely that a piece of dust will fall on it, right? Then that means the larger die size generates low yield. Okay, so that's why larger high-end chips are so expensive, because while you were producing this number of chips, a lot of them have to be discarded. And that's one thing. Now, see, these are patterns of this wafer, which part of the wafer is not working. So this is very likely a piece of hair that falls on it or a piece of long things that falls on it that makes this stripe not working. So what's going on here? This is very likely caused by a reason that your mask is slightly like a few arc second twisted. In the center, it's okay, it's not that bad. But if it's not perfectly aligned on the side, it just have no way to work. Okay. And this is probably more like something happened in center, something happened here. This is about probably some misalignments or something falls on it. But this is a very common pattern. Then it's always like this, that the center tiles are more likely to be good ones than on the side are likely to be the bad ones. Let's see what's next. Then, so what's the largest die size that we can see today? And this is also from our data set. And you can see there are a few large ones that's 1 kilo, 1,000 millimeter square. But those are they're chiplet technologies, right? We have to combine all those chips together. For single chips, that's pretty much 800 millimeter square. So NVIDIA H100, NVIDIA A100, those are all fall in this region. We have no way to continually increasing this number because of the yield difficulty. And another thing is, because the light comes from a single source, right? So it somehow needs to be scattered a little bit, right? So if it's scattered, it's not that precise. So we cannot really have each of them very large. So that's why the largest die size pretty much limits the number of transistors that we can have. The only way to increase a transistor is to make the transistor smaller. Okay, and they're doing something even more crazy. They know probably there's no way to avoid problems with those chips, right? So what they do, I don't know if you heard of this. This is a screenshot from Apple. So they sell 8-core CPU with 4 performance cores, and they sell 8-core GPU, 10-core GPU, and 10-core GPU. Why they have two different versions? Yeah.
Just to compensate for chips that like are faulty.
Yeah, that's right. So they may detect, okay, 2 GPU cores are not working. Rather than wasting it, they sell it as lower-end devices. Okay, that's why you see MacBook Air has this weird 7-core GPU design. It's probably just one GPU core is not working. Okay, and actually chip pinning is almost always there, and sometimes they even do something like this. The demand of this is really high. People like to buy low-end devices. But the yield is pretty good, that we produce a lot of these things. What they do is they just use software to disable 2 GPU cores and sell as this thing. Then there's always hacky people, they just say, oh, we can use some software to turn it off so that we can pay the price of this one, get the quantity of this one. So there's always something called a chip lottery. So you buy a chip, not all the chips are the same. They are this different and that difference, right? So even you see 10 cores, perhaps what they actually have is 12 cores. When you say 2 megabytes of cache, they probably build 2.4 megabytes of cache just for redundancy so that they can sell reasonable device. Okay, this thing is called chip binning. And sometimes this chip binning may impact performance. Let's say these 10 cores are connected with a network, right? Maybe this network, these 2 are closer to the center, faster. These 2 are away from the center, they're slower. Just examples. Then you buy a chip that the center one is broken. Then I buy a chip, the side one is broken. So they both have 10 cores GPU, but they may have slightly different performance. That can happen. Okay, then on the other side, we're talking about energy consumption. Now, what's the energy consumption today? We have this term called TDP, thermal design power. So this thermal design power is not the actual power that is designed, that's consumed by this chip. If we really want this chip to run faster and faster, if we can use liquid nitrogen as a cooling method, then we can make it consume a very high power and make it run really fast. But this TDP is designed to say, in a typical case, I want my chips to work in this way. Let's say my laptop is running some reasonable, like Figma, Microsoft Word, Adobe Photoshop, then my computer will consume 100 watts of energy. Okay, it's the suggestion for what type of cooling method we really need. So it's stuck. It's just slow. It's probably large image. So with less than 25 volts, we probably can just use passive cooling. 45 volts, we need a fan. 200 volts, we need a liquid cooling, right? It's just suggestions. But what's the typical TDP? So at early age, you see the TDP are at this range, right? And the blue ones are CPUs. The orange ones are GPUs. CPUs are rather stable, like tops at about 100. And these years, they're definitely growing. We want more and more powerful devices. Then GPUs at the beginning are only low-end GPUs. And then we start to have higher-end GPUs. And GPUs, because it's more flexible, that you always buy the whole thing from one company, like including the cooling technology, they can have much higher TDP. So typically, that the highest TDP today we see are 300 volts or 350 volts. But still, there's a limitation that we cannot have that much energy consumption. Then, so remember when we say the Moore's law, the last part, actually that part is describing this thing called Denard scaling. So what Denard scaling says, as transistors get smaller, their power density stays the same. So in other words, if I have a 80 millimeter square chip, no matter if I use 3 nanometer technology, 7 nanometer technology, or 20 nanometer technology, they should spend the same amount of energy. Okay, so is standard scaling still holding? Then pretty much if you can see, these are energy consumption, watts per billion transistors. So, and on this side is watt per millimeter square. So this thing is actually reducing. So per transistor energy consumption is reducing. Then transistor per energy consumption per millimeter square is rather stable, other than 7 nanometer technology. So these are rather old data when 7 nanometer just comes out. Then I took a new data relatively recently. It's not as good as the previous one, but as you can see here, as we increase the die size, the TDP is somehow increasing, right? It's somehow increasing as we increase the die size. So the TDP is somehow increasing. So I would say Denard scaling is not as valid as Moore's law today. So Denard scaling is seriously being challenged. And even you look at this one, it looks like it's rather stable, right? So it seems Denard scaling is there. But when Denard scaling was first introduced, it's supposed to be a device level matrix. That means no matter what we do, we don't need special technology. We build that chip will consume that energy, that amount of energy. Today, Denard scaling, if we really do that thing, Denard scaling will not hold, because we have one thing called dark silicon effect. What is dark silicon effect? Dark silicon effect means if we want to consume that amount of energy, if we want to stay within TDP, we cannot have our whole chip to be working at the same time. So we either have to turn off some cores, turn some part of memory, some caches, or we just turn some fine-grained registers off to save energy. So this is called power gating. That means we just do not provide power to part of the chip so that it can stay within the TDP level, or sometimes we even reduce the frequency. So for example, you probably have much experience. If your phone gets too hot, it feels really slow, right? So that's an example that Denard scaling may not simply hold, that we may need system level, software level technology or architecture level technology to help these things to keep holding, to help Denard scaling to keep holding. Okay, so Moore's law and Denard scaling are probably the most important guidance for the performance that we can achieve today. So I would say Denard scaling is more like a physics law. Moore's law is more like a psychology or business law. It's because people are expecting it's growing that fast, that to win the competition, I have to reach that level. And they just start to think about new method to reach that level. Okay, just a conclusion, takeaways for today's lecture. What is computer architecture? It connects the device technology with applications. It's the center of the computing technology stack. It's leading the chip design industry. So we're considering a few generations away. Then it's the backstage hero of some ultra fast chips. So you may think, oh, the power comes from smaller and smaller transistors. But to make those transistors to work, then we may face lots of new challenges. That we have to use some novel architecture solutions to solve those things. For example, power gating or fine-grained power gating. Those are all technology, architecture level technology, that we have to have those new technologies to make 7 nanometer, 5 nanometer, 3 nanometer technology to work. Okay, so next week we're going to start with combinational logic and sequential logic, and a little bit on the Boolean logic.